I have you loud and clear.
Hello. Welcome. Science.
And that is to say,
physics,
medicine,
nature,
or
space, time,
the brain,
life, the universe.
Hello, welcome to The Naked Scientists, the show where we bring you the latest breakthroughs in science, technology and medicine. With me, Adam Murphy.
And with me, Chris Smith. This week, will mass COVID testing in Liverpool get us out of lockdown, antibodies to defend the brain, and why we've evolved to laugh.
Plus, we look at Earth on the move. From our journey through space, to how tectonic plates rearrange themselves, how ocean currents bring us warm weather, and how massive storms appear.
The Naked Scientists podcast is powered by ukfast.co.uk.
With an estimated 50,000 new cases per day and, according to the Office for National Statistics, 618,000 people infected across the UK at the moment, that's one person in every 90, the country's now back in a state of lockdown.
This is despite the UK having one of the highest testing capacities in the world now. Over 20 million tests have been carried out, more than double the number in France, Spain and Italy. But the reason that the coronavirus is so hard to get on top of in many countries is because in more than half of cases, the infected person has no symptoms. And because we only test and follow up the people who have symptoms, we're missing the majority of cases.
One answer is to just test everybody, and that's the experiment that's now going on in the city of Liverpool. Mass screening of the entire city to flush out and isolate infectious cases and hopefully rein in the outbreak. So how's it going to work? What will it prove? And what's the evidence from other countries that this might be the right way to go? I spoke to epidemiologist at the London School of Hygiene and Tropical Medicine, Julian Pito.
The purpose of mass testing is to identify people before they've infected anybody else, then to lock their households down and also to trace their contacts rapidly.
Why have they decided to do this in Liverpool now?
Because Liverpool's got the highest rate in Britain, so you're testing the approach and addressing an urgent public health problem. The difficulty is that they're launching it within a couple of days of starting lockdown, and of course the infection rate's going to drop very fast anyway as a result of lockdown, so it's not clear that they'll get very good evidence on how well it's working.
We know that this has been done. China have famously now done this on the scale of millions. They're taking cities with 9 million people in them in some cases and testing the lot in under a week. So how are they doing it? And if they've proved it works, why aren't we already doing it?
Well, they weren't doing regular testing. They tested the entire population of the city, but they already had all sorts of stringent sort of testing and tracing and lockdown processes going on. The idea that I've been plugging for a long time is that if you test everybody once a week, you could just end lockdown. You'd reduce the rate of transmission so much that we could all go back to the pub and start going to football matches and kissing our grannies.
How are they actually going to do this in Liverpool? What's going to be the mechanism for doing these tests?
People simply volunteer to get tested. I mean, some groups, such as NHS workers and so on, are being targeted, but they're also inviting anybody who wants a test to simply go to a testing centre and have one. They're using what are called point-of-care antigen tests, which are tests which are done on the spot and give you a result within, well under an hour. That's one of the problems with the demonstration project. I mean, you want to try and test the whole population, not just people who turn up to get tested.
Slovakia have been doing this as well, haven't they, in recent days? They have tested at enormous scale a very large number of people and picked up a significant number of people who both did have symptoms, but equally those who didn't.
They tested 3.5 million out of a population of about 5.5 million over a couple of days, and they're going to repeat it a week later. They found that 1% of them were infected. It'll be interesting to see what happens when they do it a week later. Simply doing it twice over 2 weeks, I mean, like the intervention in Liverpool, which is the same thing, it can knock it down, but of course it won't have any subsequent effect. It'll creep back up again afterwards. You've got to keep it going for 3 or 4 weeks at least to bring it down to such a low level that you can then do it less frequently or reintroduce it every month or two as it starts to creep up again.
Thinking about the practicalities then of doing this on the scale, not just of a city like Liverpool, but if it's going to be useful, we're going to have to do the whole country, aren't we? And we're going to have to do it regularly. So in practical terms, can we lay our hands on the sort of testing capacity that we need. And how much is this actually going to cost?
As far as the testing capacity goes, by far the cheapest and the quickest way of getting the capacity you need, which is 10 million tests a day, is a method called LAMP testing. It's a simplified version of the PCR testing that they're using already.
And how long would we have to keep doing this for?
I don't think you need to do it for more than 3 or 4 weeks. You might have to do it again a few months later. You wouldn't just go on doing it. I mean, once you've got the infection down to, 1 in several thousand, you'd obviously slacken off and then perhaps reintroduce it later. But it's much nicer to reintroduce mass testing every few months without any lockdowns than to introduce lockdowns every few months.
So the strategy, therefore, would be you take in the entire country, you test everybody, you pick up en masse, all at once, all of the infected cases, whether symptomatic or not, and you isolate them. And because you're doing that all at once en masse, you are breaking the transmission chain there and then, and that will translate, you're saying, into a big reduction in cases, which buys us a big window, effectively, of low levels of virus, and we're effectively almost back to normal, at least for a while.
Yes, I mean, it's a permanent strategy for keeping going without destroying the economy until a vaccine becomes available. For a vaccine to be available for the entire population is going to take a long time. I'd be very surprised if everybody's going to get vaccinated within less than a year.
It sounds like a really compelling case. So why have the government, not just of this country, but many countries, not pursued this more aggressively?
There are a whole series of reasons. I mean, first of all, it's never been tried in any country ever, testing the whole population once a week to control a pandemic like this. Secondly, there are very strong vested interests involved. I mean, the government's allocating very large contracts for testing and tracing. The method that I'm recommending would be run without their involvement. One rather irritating thing is that the expert modelers who've been advising the government didn't think of it themselves, and so they reacted by saying it was a rotten idea, although there's never been any serious scientific objection raised.
So let's wait and see what happens then in Liverpool, nevertheless. Julian Peto there.
Well, to a different kind of infection now, and that's how the brain keeps itself safe. Our brains sit cocooned inside a series of protective layers. They're called the meninges, and these, together with a structure called the blood-brain barrier, keep out unwanted bugs and nasties that could otherwise prove lethal for us. But how exactly the brain's defence systems do this wasn't known. Now, a new discovery has added an important piece to the puzzle. Specialised plasma cells, these are blood cells that make antibodies, learn to recognise important, potentially harmful bacteria in our intestines, and then they make their way up to the outer part of the meninges, called the dura, where they churn out antibodies and keep the brain bug-free. Menna Clatworthy.
The thing that really got me interested in thinking about the brain is that there's increasing evidence that the immune system plays a role in a number of brain disorders. So things like depression and anxiety, and even the progression of neurodegenerative diseases like Parkinson's disease. As well as that, we know that the immune system is required to defend parts of the body from infection. So this could be important for defence against infections in the brain and in the meninges. So things like meningitis.
How did you then pursue this to try and work out how the brain was actually fending off infections?
As with many studies in immunology, we use mouse as a model. And so the first thing that we did was to take meninges and look at them under the microscope. And there were plasma cells in the dura, and they were not just scattered anywhere. They were actually lined up along the border of large blood vessels that run through the dura. These blood vessels are called venous sinuses. The next question, when we found these plasma cells, was what antibody they were producing. To our surprise, we found that rather than producing IgG, what's normally found in the body, they were actually producing IgA, an antibody that's normally found in the gut.
So you've got this interesting observation, sort of anatomically in the first instance, of blood vessels running through the meninges. They've got cells that make antibody lining up along them, but the antibody they're making is one that you would not normally associate with the bloodstream. It's one that you would find in the intestine.
Yes, so that was surprising, and I guess the next question was, well, do these cells actually originate in the gut, or are they influenced by the gut? So to answer that, we were able to use mice that have never seen any sort of bug. They have no bacteria or any microbes in their intestine. And when we looked at the dura from these animals, there were no IgA cells whatsoever. But when we added bacteria back into their gut, suddenly again the antibody-producing cells reappeared in the dura. And even if we only put one type of bacteria into these mice, a type of bacteria that couldn't go anywhere other than the gut, we still saw these cells reappear in the dura. So that told us that those cells originated in the intestine.
Your sort of hypothesis then is that the bacteria go in the intestine, they educate the immune system and immune cells in the intestine, and what the cells then migrate from the intestine with the knowledge of how to make antibodies against those specific microbes up to the brain and take up residence in the meninges around the brain.
Exactly, and they specifically take up residence at the border of these dural venous sinuses. And I guess then the obvious question, well, why? Why would that happen? Why has this system been set up? And the obvious answer would be, well, maybe those cells are there to protect the brain from microbes, bacteria that originate in the gut but get into the bloodstream. And when they're flowing through those venous sinuses where blood flow is quite slow, it's an opportunity for the bugs to get out into the brain. So to test that, what we did was to remove all of the antibody-producing cells, and then we challenged mice with microbes into their bloodstream. And what we found was the bugs were able to get across into the brain. So it told us that really we'd found a whole new defense system for the brain.
What are you going to do next?
We're interested in the signals that might take the plasma cells from the gut to the meninges. And then the other thing I'm really interested in is whether this has implications for how we try and protect people from meningitis. At the moment, if we vaccinate against meningitis, we give that vaccine into the muscle. But our study would suggest that actually if you want to make cells to defend the brain, the route that you should give that vaccine is actually via the gut. And so that's something that we're looking into.
The body's a clever old thing, isn't it? Menna Clatworthy there, she's based at Cambridge University. Her study describing that work has just come out in the journal Nature.
Why do kittens, puppies and human animals play? From pets rough and tumbling with each other to team sports. Join me, Katie Hayler, as I find out why larking about is so important for health. Check out Naked Neuroscience on the Naked Scientist website or wherever you get your podcasts.
This is The Naked Scientists, and it is Adam Murphy and me, Chris Smith, here with you this week. And on the way, why we've evolved to laugh. And we also follow our planet on the move. What's the Earth's surface going to look like in millions of years' time?
But first though, in countries like the UK, about 2% of people over 40 have the eye condition called glaucoma. This is where pressure builds up inside the eye and damages the optic nerve. Untreated, it causes irreversible blindness and is a major problem worldwide. Now, researchers have come up with a way to use gene therapy to stimulate the damaged optic nerves to regenerate in experimental animals with the condition. Veselina Petrova worked on the study at Cambridge University and she's with us now. So, Veselina, could you tell me a little bit about what it is you've achieved?
In our study, we looked at the ability of a molecule called protrudin to promote regeneration and repair of the injured nerves. And we've used 3 different models to test this. In one model, we grew nerve cells in a dish and injured them using a laser. And in 2 other animal models, we actually used the optic nerve damage to look at the efficacy of protrudin. The optic nerve is actually the nerve that connects the eye to the brain and which relays visual information. And what we found in our study is that in all 3 models, delivering protrudin to the nerve cells actually improved not only their survival, but also their repair and regrowth after injury.
Could you tell us what protrudin is then?
Yeah, protrudin is a protein which is normally found in the cells. And what it actually does is it acts as an adapter protein, and it brings together a lot of things that are important for growth and concentrates them exactly at the area that they're needed at during growth after injury.
And then when this chemical is in cells in the eye, it means it regenerates them and makes them live longer. Is that right?
Yes, that's right.
And then how do you know that it works? Mice are hardly famous for their eyesight.
Yeah, that's true. We are currently doing further studies to actually look at the functional output to see whether they can regain some of their vision back. But this is some of the greatest regenerative effect that we've seen with any treatment in our lab. We believe that such a massive outgrowth, if we can make these nerves grow back to their target areas in the brains, then that could really help functionality. But we're currently studying this.
Do you know if this is a long-term effect or is it just temporary?
So we've only looked in our mouse models for several weeks after injury, and we could see really sustained effect. In humans, of course, we have to test this, but there's currently some treatments that have been licensed specifically for the eye, and they really show that if you deliver gene therapy to the eye, that leads to a long-lasting effect. So we hope to see a similar thing with our gene therapy approach.
And how likely is something like this to work in humans?
There's already treatments that are available in the UK that include gene therapy in the eye, and there's several others that are underway in clinical trials. So gene therapy does work in the eye. How likely our treatment is to work in the eye? As I mentioned, we've only tested this in animals, so there is a lot of further work needed to see whether, first of all, it's safe, also effective in humans. But we're really hopeful that even if it isn't, we've discovered a new pathway involved in the process of regeneration, which could potentially provide some targets for pharmaceutical treatment.
What about other conditions where there's nerve damage, like spinal cord injury? Could a similar kind of approach work there?
We tested this in the eye, but the eye is part of the central nervous system and the optic nerve is part of the central nervous system. And nerves of the spinal cord and the brain are also part of the central nervous system. So we believe that similar processes are happening in all these systems, and possibly we could apply what we found in the eye to the spinal cord and the brain. And we're actually doing these studies in our laboratory right now. So hopefully I'll have an answer for you later on.
How do you actually get this protrudin into the eye?
We use viruses which have been inactivated, so they're not infectious. We just take the outer coat of the virus and package inside the gene, and then we trick the cells of the brain thinking that the virus is infectious. So they take up the virus and the DNA is released and integrates into the eye cell's DNA. So it's kind of like a Trojan horse, if you think about it. We just trick the brain to think that the virus is infectious, but it's not actually. We just use it as an approach to deliver the gene to where we need it.
Veselina Petrova, thanks very much. And her paper has just been published in the journal Nature Communications.
Terrific piece of work and something certainly to smile about. But from smiling to its counterpart, laughing. It's a bizarre thing, isn't it? The sounds that we make when we laugh, the faces we pull when we do it, and it doesn't really matter where around the world you go. We all do it. So why have we evolved this way?
Well, that's the question that Edinburgh University evolutionary ecologist Jonathan Silvertown takes on in his new book. That's called The Comedy of Error: Why Evolution Made Us Laugh. Katie Haylor heard what he had to say.
We laugh in response to humour. So what is humour? And people have wrestled with this for a very long time. It turns out that modern science can pretty much answer this question, but nobody has yet actually put it all into a little book. So I did. You might think of humour as the stimulus and laughter as the response. Immediately you put it like that, it kind of fits into the standard language of describing behaviour. Laughter, in the broader context, is it something called a play vocalization. Most of the laughter you'll hear during your working day will be nothing to do with jokes. It'll basically be the noises that people make when they are communicating with each other in a friendly way. It's very much a social thing. So it turns out that rats laugh in social situations. They modulate their laughter as well. Scientists taught rats to play hide and seek. Apparently it takes 2 weeks to teach a rat to play hide and seek. And it turns out that when the rats are hiding, they stay quiet. And when they're seeking, they laugh. So human laughter is a play vocalization. It's something that is found throughout social mammals, so far as we know. That means, from an evolutionary point of view, that it must be really ancient. It must go back to the common origin of mammals, or at least social mammals, and that makes it tens of millions of years old. Certainly verbal humour can't be any older than language, maybe 1 million years. It's not 20 million years old for sure. So laughter evolved first. And at some point during our evolutionary history, laughter became attached to humour. Whereas most of the laughter you hear is essentially a kind of social lubricant that says, we're having a good time, it's all fine, don't worry if I say something a bit cheeky, I'm just joking. In the case of rats, it means if I'm chasing you, I'm not attacking you, this is just play. But when it became attached to humour, it did something else. But what is that? And why did it happen? And what good is it? And those are actually all the things I address in my book.
Is there anything to be learned in the difference of laughs? Because, you know, if you're really finding something funny, you might do a big belly laugh, or maybe there's a sort of...
There is the natural laugh and there is the forced laugh. We can all tell the difference instantly. And that is very interesting from an evolutionary point of view as well. It's difficult to fake laughter that other people will believe is real. I mean, that's the other thing that demonstrates this is really very much a biological phenomenon, is its universality. It's found in all cultures.
Is there an evolutionary benefit to laughter? Is this about getting on better with people or being less of a threat?
So if we're talking about evolution, it can be good for survival and it can be good for reproduction, or both, actually. I'm now not talking about the contemporary world of human evolution, but anciently evolved characteristics. Clearly, there was something in the first place that favoured laughter as a play vocalization. Okay, it's a signal that makes life safer.
Is there a reproductive benefit to being funny?
My hypothesis is it's all about sexual selection, demonstrating how clever you are. Being clever in a clever species is sexy. How do you find out if they're clever? Or more importantly, how do they convey to you that they are genuinely clever? Well, there are various ways. You can give lectures and become a professor, but that takes a long time, by which time you'll have children. Or you can tell a joke. To be a good signal of anything, it has to be unfakeable. Laughter is very difficult to fake, but actually so is genuine humour. If you make a joke that falls flat, do you feel an idiot, right? It's a pretty good sort of rule of thumb for intelligence. Cross-cultural studies, something like 50 different nationalities. In all of them, if you ask people what they're looking for in a mate, good sense of humour comes in the top 3, both for men and women. Sexiness is pretty well established. It's pretty universal. So there have been experimental studies which suggest that it does actually work. But to answer the question, you know, what good is humorous laughter? We have to think differently. So people have tried to answer this question for at least 2,000 years. It's something Aristotle wondered about. These days, the people who study the subject, and comics as well, I think by and large, come down to the idea that it's all about incongruity, the difference between what you expect and what actually happens. Darwin said that basically there's incongruity, you mustn't feel threatened in any way, surprise helps, and being young helps, basically. That he said that, you know, he's observed many a time I've observed young people who seem to be laughing for no good reason. I'll give you a joke. I went to the zoo the other day. All they had there was a dog. It was a Shih Tzu. If you happen not to know that there was a dog called Shih Tzu, you wouldn't find that funny at all. So jokes depend upon culture, upon knowledge, upon processing. And that's why they're subjective, or one of the reasons anyway.
Jonathan Silvertown there speaking to Katie Haylor on why evolution makes us laugh.
Well, it made me laugh. I've got one for you though, Adam, right? You're a physicist. What is a nuclear physicist's favourite meal?
Ooh, what is it?
Well, fish and chips, of course.
But
The Naked Scientists podcast is produced in association with Spitfire, cost-effective voice, internet and IP engineering services for UK businesses. Find out how Spitfire can empower your company at spitfire.co.uk.
Music in the programme is sponsored by Epidemic Sound, perfect music for audio and video productions.
Throughout November, we are musing over movement, from tiny cells at one extreme to orbiting planets at the other. And this week we are looking at our own planet, Earth, where many things are in motion around us, from the air we breathe to the water in the oceans and even the stars in the sky, and we're going to hear about all three.
Indeed, the Earth's spinning and we are whizzing around the sun at a dizzying speed, and the Earth's also tilted on its axis, and those factors all make a world of difference to what life's like for us here on the planet's surface. Well, let's put some numbers on all of this. With us from Cambridge University is space scientist Matt Bothwell. So, Matt, how fast are we whizzing through space?
I guess the answer is it depends which way you look at it. The Earth is rotating, and we're rotating at about 1,000 miles per hour if you're standing at the equator. But the Earth is also orbiting around the sun. So if you zoom out a bit, we're traveling at about 100,000 kilometers per hour around the sun. So somewhere between fast and very fast, depending on which way you look at it.
And of course, it doesn't stop there, does it? Because the sun is on its own orbital journey around our galaxy, and our galaxy is on its own orbital journey around its cluster of galaxies.
Exactly, yeah. The Milky Way is rotating once every couple of 100 million years, and we are travelling at around 200 kilometres per second around the centre of the galaxy, which is just a phenomenally large speed.
So it's quite hard to actually say how fast we really are moving through space.
Right, exactly. You always need to define it relative to something, right? If you're travelling in a car along a road at 60 miles an hour, you're defining your speed relative to the road. It's all about what you're travelling relative to, I guess.
But returning to our cosmic neighbourhood and how this affects life on Earth for us, why do we have a seasonal pattern to the weather?
So that's all about the Earth's axial tilt. So the Earth isn't actually straight up in space. The Earth is a bit wonky. We've been knocked off straight axis by about 23 degrees. That's actually the evidence of an ancient impact. So billions of years ago, the Earth was struck by some kind of big body in the solar system. It's the same impact that formed the moon. And ever since then, the Earth has been wonky by about 23 degrees. And that's why we have our seasons. So as we go round and round the sun, the northern hemisphere in one part of the cycle, and then the southern hemisphere 6 months later in the other part of the cycle will be pointing towards the sun, and will therefore get more sunlight and will experience summer. So we only have seasons because of this axial tilt.
And is that axial tilt stably wonky, or does it wobble around?
It actually wobbles around. So there is a 26,000 year cycle where the Earth's axis wobbles around a bit like a spinning top. If you imagine setting a spinning top going and seeing it kind of slowly rotating around, that's kind of what the Earth does. So over about 26,000 years, the Earth's axis rotates around. It's called the precession of the equinoxes. And because of that, the night sky actually shifts. So Polaris, for example, is the North Star right now. It's the star that is above the Earth's axis. If we wait a few thousand years, the Earth's axis will have shifted around and Polaris will no longer be the North Star. About 5,000 years ago, when the pyramids were being made, we had a different North Star, and we'll have a different North Star again in the future. It's kind of amazing. The night sky shifts above our head because of the Earth.
Yeah, boggles your mind that, doesn't it? Given that the Earth is tilted, but that tilt, you're saying, wobbles about, does the wobbliness with this 26,000 year cycle translate into climate changes with a similar sort of cycle?
Yes, it absolutely does. There are these things in climate called Milankovitch cycles, and these are the cycles of the climate that are caused by the Earth's motion in space. As the Earth travels around the sun, sometimes it's always a bit more squashed, and sometimes it's a bit more circular. And the wonkiness of the Earth changes over this 26,000 year period, and then so over hundreds of thousands of years, yes, the climate changes because the Earth is orbiting in very slightly different ways around the sun.
And if we come down and sort of land on the Earth's surface for a moment, you did start by saying the Earth is spinning pretty fast. First of all, why is the Earth spinning pretty fast, and what effects does that have?
So the Earth is spinning for the same reason that the Earth is orbiting the sun. We've inherited the primordial spin, if you like, from the cloud of gas that formed the solar system. If you go back billions of years, before the sun and the planets existed, there was a big cloud of gas, and gravity squashed everything down and formed the planets and the sun. In physics, we have a thing called conservation of angular momentum. Basically, if something starts spinning, you can't get rid of that spin. And so any little bit of spin that gas cloud had originally would be inherited by the sun and the planets. And so that's why the sun is spinning, the planets are spinning, and they're all orbiting the sun. It's all the leftover spin from that original gas cloud.
And what effect does that spin have on things on the Earth's surface? For instance, the atmosphere, for instance, the oceans and the seas?
So there's an effect called the Coriolis effect, which is basically caused by the fact that at the equator, that's the fastest you can spin. And the higher latitude you go, or the lower latitude towards the South Pole, you're actually spinning slower and slower. And if you imagine standing near the North Pole or the South Pole, you'd be going around very, very slowly. And that causes all kind of interesting effects in the atmosphere. For example, if you have air going from lower latitudes around the equator up to higher latitudes, it's going to be traveling much faster than the air up in the north. And so that is going to cause all kinds of interesting cyclic effects in the atmosphere and the ocean. And so a lot of what the Earth's weather is doing is caused by this Coriolis effect, which is basically a result of the Earth spinning round.
And that would be why storms spin. Characteristically, when you see them on satellite pictures, they spin one way in the northern hemisphere and the other way in the south hemisphere.
Exactly, it's wonderful. When you see pictures of Earth from space, you can see cloud formations, which are just showing you these forces caused by the Earth's rotation, just kind of written in the clouds. It's kind of beautiful.
It's amazing to think that all that stuff going on in space, all those billions of years ago that gave us our planet, now gives us our weather patterns today. Matt, thanks very much for joining us to fill us in. That's Matt Bothwell from the University of Cambridge. Now, back on the planet's surface now, and you have to consider the Earth under your feet, because that's been through some pretty massive movements over its time as well, and it's going to carry on doing so, as Adam has been hearing.
The Earth under our feet is not as solid or as static as we might imagine. The top layer of the Earth, the crust, is cracked into pieces called plates, and those plates are floating around on top of the layer underneath, which is the mantle. And as old plate sinks back into the mantle, new plate is made elsewhere, because the Earth isn't shrinking. But how does that all work? I spoke to Hannah Sophia Davis from the University of Lisbon about how the Earth moves and what the future might be.
There's plates being made and destroyed. So where the ocean is being made is at a mid-ocean ridge. The big mountain range you see in the Atlantic, on maps of the Atlantic, that's where plate is being produced. And then where plate is destroyed is in these subduction zones. So you see that in the Pacific Ring of Fire, this big ring of subduction zones where ocean plate sinks back into the Earth and destroys it. As the plate sinks into the mantle, it pulls plates along with it. And so essentially the continents float around and they're being pulled and pushed by the ocean plate as it's being made and destroyed. And that's essentially how the plates move.
But if everything is always moving about, what did things look like hundreds of millions of years ago?
The Earth used to be in a supercontinent state, and it tends to cycle between supercontinents and dispersed continents. And that's because oceans are always pushing and pulling as the subduction zones are destroying and ridges are creating ocean. And this has happened several times in Earth history. Pangaea formed around 300 million years ago and broke up around 180 million years ago. And when it broke up, it actually formed the Atlantic Ocean. And so that's why you can see that kind of jigsaw fit between the Americas and Africa and Europe, because that's still the remnant of the Pangaea. You can see where Pangaea used to be.
We used to have one big continent then, with everything smooshed together called Pangaea. But what does the future hold?
Most geologists will tell you the Pacific is due to close and the Atlantic is due to continue opening. It has this very large mid-ocean ridge that is still producing a lot of ocean plate. Logically, the whole thing should kind of turn inside out, and Pangaea should reform over the Pacific Ocean, and this new supercontinent is Novo Pangaea. So a new Pangaea.
That is basically what will happen if everything continues along business as usual for a few 100 million years. There are other options, though.
Obviously, the Atlantic doesn't have to continue opening, and there is evidence that it might not. This could mean that subduction zones start spreading around the edge of the Atlantic, and eventually we have an Atlantic ring of fire that will end up closing the Atlantic too. And so Pangaea could end up coming back together. In that situation, we just have another Pangaea.
Could it get even stranger? What happened if the Atlantic and the Pacific both closed up?
Ocean plate starts to get more dense as it ages. So it really should start sinking into the mantle after around 180 million years. The Atlantic is currently getting to that age, and the Pacific is long past that age. We can envisage a scenario where both oceans close, but if you think about the surface area of the Earth, obviously you have to retain that surface area, so a new ocean has to form. And the theory is that there is a rift in Asia which will split to form a new ocean. And that's the Orica scenario. So essentially, the Atlantic and the Pacific both close, and we just have a completely new supercontinent, which looks nothing like any of the other supercontinents, and a completely new ocean, which is from the breakup of Asia.
There is one last idea. If you look at a globe, you might notice how compact everything is up around the North Pole, and how small the Arctic Ocean is.
There is a theory that supercontinents like to form 90 degrees away from the next supercontinent because Pangaea existed for a long time, and it was a very large continental mass, and essentially it kind of left a bit of a scar in the mantle. As supercontinents, when they form, geophysicists think that this scar will affect where the supercontinent forms. So the fourth scenario that we have kind of out there to propose what the next supercontinent will look like is the Amasia scenario, and that's essentially just that all of the continents will just kind of smush together in the northern hemisphere.
And I suppose that would mean that beachfront properties could be at a real premium in the future. Hannah Sophia Davis there.
This week we're looking at Earth on the move. Still to come, how do hurricanes get going?
Now, we may call this planet Earth, but its surface is mostly water, and fueling giant ocean currents, that water is constantly on the move and has huge impacts on the climate and environment. Eric van Sibyl is an oceanographer from Utrecht University, and he's with us now. So, Eric, what are the biggest currents that we've got in the ocean, and what is it that makes them?
Yeah, so you may have heard of the Gulf Stream or the Kuroshio of Japan, or maybe the East Australian Current of Sydney. And those are what we call western boundary currents. And they are the western boundary currents of giant gyres. Gyres are gigantic basin-spanning swirls, essentially. There's one in each ocean basin, so there are 5 in total. And the highest speed in each of these gyres is not much more than walking pace. And most of it is much slower. So it takes maybe 5 years or so to do a total loop around one of these gyres. And what are they forced by? Well, the gyres are forced by the winds that are blowing over the ocean. And then in particular that there are the easterly flowing trade winds near the equator and the westerly flowing winds at the subpolar latitudes. And all of this creates those gyres. But really the biggest current of all is the Australian circumpolar current, as we call it. It runs from west to east around Antarctica. It is more than 2 kilometers deep. It is hundreds of kilometers wide. And in total, it transports 150 million cubic meters per second. And that is roughly 100 times more than the combined outflow of all the rivers in the world.
Wow, that's huge. And you mentioned there the Gulf Stream. So what is that? How is it formed? And what does it do for us?
Yeah, exactly. So the Gulf Stream is the western side of the North Atlantic gyre. It's on the eastern side, of course, of the US, but as oceanographers, we like to have an ocean-centric worldview, right, where we look at the ocean itself. Now, that each basin, like the North Atlantic, has a western boundary current, as they call it, a current on the west, has a beautiful mathematical proof, and it's called the Sverdrup solution. And in short, it has to do with the rotation direction of the Earth, and the fact that the Earth is a sphere and not an infinite cylinder, so that actually the rotational speed varies with latitude. Now, because of that, really the only possible mathematical solution is a gyre with a very strong current on the western side. But note that the Sverdrup solution, that can't actually explain why the ocean is the way that it is, because yes, it explains the western boundary currents, but on top of those large-scale gyre flows, the ocean is also chock full of what we call eddies. Now, eddies are much smaller vortices, maybe a few hundred kilometers in diameter or so, and they are kind of like the bubbling, turbulent nature of the entire ocean as it moves around.
And another thing people might have heard of that they might not be too sure of, I know I'm one of those people, you sometimes hear about something called El Nino in the news. What is that and what does that do?
Yeah, so El Nino is not per se about currents. El Nino is a massive redistribution of heat in the tropical Pacific Ocean. So sometimes, and especially during what we call La Nina periods, the heat goes from the atmosphere into the ocean. And that means that worldwide, the atmosphere cools a little bit for a few years. And then during an El Nino, the heat comes back and the atmosphere warms up extra fast globally. So this is really a measurable effect. While winds are certainly important in El Nino, it's not really connected with the current. So I guess even if the ocean would not move, there would still be things like the El Ninos, I think.
Those ocean currents you mentioned earlier, they're not exactly clean, are they?
No, I know what you're speaking about. They're not clean at all. The ocean currents carry enormous amounts of plastic around. And what happens actually is that within the gyres, so these 5 gigantic swirls around the ocean basins, the flow is actually slowly inwards. So as the flow spirals slowly inwards, the plastic goes with it until then in the middle of the gyres, so in the centers of the basin, the water sinks down a little bit. But the floating plastic is, of course, too buoyant, so it stays behind. And as new plastic then spirals in, there's a constant more and more plastic piling up. It's a bit, I guess, like the turd that won't flush.
And then how are things going to change as we see the climate changing more and more?
Yeah, so that's the big question. So the ocean by itself is absolutely going to change. And that is, of course, the sea level rise that we know. That is the ocean warming up, the ocean becoming more acidic because CO2 is actually captured within the ocean. So 25% of all the carbon dioxide that we've burned as society has gone into the ocean. It's a bit as if we get a 25% discount on our fossil fuel emissions. So that is all absolutely happening. But what the currents are doing is a little bit less clear. Now, we know that winds are probably going to be intensifying. So you would expect the gyres to spin up a little bit and to go a little bit faster. And that probably means that they also become more unstable. So probably more eddies. But exactly what that then means, we don't know. So it's a bit unclear. We don't even know about the large scale, kind of like what we call the thermohaline circulation, where all the ocean basins are connected and where heat is redistributed between the gyres rather than the flow within the gyres. We don't even really know what that is going to do in a changing climate. So, as oceanographers, we have a really difficult time to predict what will happen. We don't have much evidence from the past about the strength of the currents per se. So what exactly it is, we just don't know.
Eric van Sebille, thanks very much.
Now, so far we've looked at the earth, we've looked at the water. Well, now we're going to look at the wind and the air that keeps us alive, of course. Now, 2020 was a record-breaking year for storms across the Atlantic. There were dozens of named storms and cyclones spawning and making their way across the ocean. But how do they get going in the first place, and why are some of them more energetic and destructive than others? Connie Klein is at the UK Centre for Ecology and Hydrology. So kick us off, Connie, and tell us first of all, how does a big storm brew up in the first place?
So tropical cyclones over the Atlantic, they generally develop from tropical disturbances over Africa. And those disturbances are thunderstorms that are just packed together to a cluster. And they travel with an area of low pressure over the continent. And those disturbances are actually the seedlings for tropical cyclones, of which hurricanes are just a very extreme version. So those disturbances, they can strengthen over the Atlantic once they left West Africa, and they might develop into a hurricane when some ingredients are present in the atmosphere. But probably the most important ingredients is the warm, moist air over the ocean as a fuel for the storm. And such conditions we actually only find over tropical oceans with an ocean surface temperature of about 26 degrees and above. And so when the tropical disturbance moves over the ocean, it's sucking in air towards this low pressure center that already exists. Areas moving from high to low pressure. This air is sucked in, it's warm and moist, and this basically just comes from the evaporation of the very warm ocean. And once this air is lifted, in the case of a hurricane development, actually, this air is highly unstable. So it continues to rise into this disturbance. And unstable really means that the rising air parcel remains warmer, which means it has a lower density than the surrounding air masses. And it rises more rapidly into this storm, the greater the density difference to the surroundings is.
So the key ingredients then are you need something like a seed crystal. You get your initial storm over Africa, some disturbance. Yes. And when it meets this killer combination of some nice warm seawater, which is warming the air above the water and making it saturated with moisture, it's that combination that then really accelerates things, and you end up with a hurricane brewing off the back of it.
Yeah, exactly. So what is actually then happening is once this air gets moving into the storm, because the air is so moist, it releases additional energy from the water vapor in the air, because water vapor is basically stored energy that was needed to evaporate the water from the ocean, and is then released once the air rises and cools. It's released again in liquid water droplets.
It's like the reverse of sweating, isn't it? So when you sweat, you rob energy away from the skin to turn your sweat into water vapor. When it turns back into a liquid in the atmosphere, it gives you extra energy, and that's going to give the hurricane an extra thump. Yeah. So it's reverse sweating for your hurricane. But what are the implications then for climate change? Because obviously if the killer ingredients are high levels of sea temperature, sustained high sea temperatures, does that mean then that if we warm the world up, we're probably on a course for more hurricanes with more intensity more often?
Yes, so the biggest factor that is also pretty likely to change rainfall intensities and hurricane intensities in general is just the higher water vapor content that we find in a warmer atmosphere in the future. So by every degree that we warm the atmosphere, we actually increase the water vapor content, the water the atmosphere can hold, by 7%. And that also means the atmosphere can rain out more water. And also there's more energy to actually be released in hurricanes. So that would drive stronger circulations. And that's very likely to happen. But
so it's a double whammy then in some respects, isn't it? You're going to get more intense storms more often, but they're also potentially capable of dumping more rainfall when they do make landfall.
Yes, absolutely. And also stronger winds. Yeah. So those two factors are very likely to happen. What is not very clear yet is whether we will see a higher frequency in hurricane numbers overall, but it's quite likely that of the hurricanes we get, a higher proportion is quite extreme.
Have we got any evidence that this is the case? Because obviously the Earth has gone through patterns of changing climate over many, many thousands to millions of years. Is there evidence that what we're predicting with climate change has happened in the past, with higher temperatures mean higher storm intensities and frequencies, and therefore more destruction?
Yes, unfortunately, the past sort of observations of hurricanes are not that dense or reliable that we can sufficiently or robustly relate it to anthropogenic forcing. But since the 70s, we actually have observed an increase in very extreme hurricanes above the category of 3, so the ones that are really destructive. And otherwise, we see this sort of behavior in models and projections, yeah.
Can you tell us, Connie, the intriguing thing about how these storms get their names?
Tropical cyclones generally get a name when they develop winds that are stronger than 60 kilometers per hour. And then they might develop into hurricanes, and that's when they reach 120 kilometers per hour. So the World Meteorological Organization actually has lists for that, and it's 6 lists. They are being rotated over 6 years, and it's very boring, actually. It's an alphabetical sort of order of names that was,
Well, one name that's definitely not boring is Connie Klein. Thank you very much, Connie. So I think I can summarise by saying we live in a very dynamic world where our planet's whizzing through space, wobbling as it does so, and it's steadily rearranging its surface. We've heard about that. Those wobbles and those rearrangements make changes in climate, and those in turn affect how our oceans behave, and then that leads to storms being born more often. You could say we're certainly a world on the move. Adam.
And just before we finish, it's time for Question of the Week. And this week, a question that's really been growing on Phil Sansom, who found the answer to this question for listener Kevin.
Does water in my veggie garden in the morning mean that the water uptake will coincide with the intake of sunlight and so give my vegetables the best chance? Or is it just as good to water in the evening?
In many ways, it doesn't matter too much when you water in regards to the happiness of your plants.
That's Anthony Bridgen from Cambridge University's Sainsbury Lab. Anthony, thanks for answering this week's question. Next week's question, meanwhile, comes from... No, hang on. Kevin, I'm sorry. That's not the end of the story. There are a few considerations here. First, when you water might change how much water evaporates away instead of getting to the plant.
If it's the height of summer, you certainly don't really want to be watering your plants in the middle of the day. A lot of the water that we're applying to the soil will then just evaporate straight off and be lost, and the plant won't be able to use it. Additionally, their ability to utilise the water they are getting might be less.
There's a common myth here as well about leaf scorch, that water magnifies rays of sunlight to actually burn the leaves. Apparently that's not true. But midday is still not a great time to do your watering.
Watering in the morning is a good choice because evaporation from the soil will be lower because temperatures are lower in the morning. Watering in the evening has most of the same benefits, but there are a couple of things we do want to think about, particularly if it's cold. If there are water droplets present on the foliage, these can have small particles and bacteria which can act as points around which ice crystals can form.
Evaporation from the soil and frost aren't the only considerations. Guy Barter, chief horticulturist at the Royal Horticultural Society, points out that plants themselves might run into the most trouble in the heat of the day.
If plants are short of water, they'll shut down in the midday heat and sun in summer. Watering in the morning before they get to that midday deficit is effective. It's also worth mentioning, when they shut down, the damage has actually been done. So watering in the morning to head off soil moisture deficit is actually a good idea.
Kevin, morning seems to be your best choice, but don't beat yourself up if you can't get up with the sunrise, because Guy agrees with Anthony that this is kind of much of a muchness.
In real life, gardeners take advantage of the fact that plants have evolved over millions of years to be extremely good at coping with lack of water. Under these circumstances, watering in the evening is good enough. You're only topping up the soil to keep the crop stress to reasonable levels. You may see a bit of wilting in the middle of the day, which is regrettable, but no, it's not a perfect universe and one has to put up with a certain amount of stress in real life.
Life lessons for us all, I think. Thanks Guy Barter and Anthony Bridgen. Next time, what's in a name? We're answering this question from listener Beata.
If 300 years ago there was one person with a certain surname, how many people could have their surname today?
So can you help us out with this mathematical mind wrinkler? If so, you can join in the discussion on our forum. You'll find that at nakedscientist.com. Or if you've got a question of your own you would like to ask, why not send it in to chris@thenakedscientist.com. There's also a web forum. There's also a web form you can use, nakedscientist.com/question.
And that's all we've got time for. Next week, it's people on the move that we'll be looking at, from the fossilised remains of ancient human migrations to the future of coping with extreme sea level rise. We are exploring the restlessness that's part of the human experience. And if you're a fan of the show, why not leave us a review wherever you get your podcasts? We really love hearing your thoughts and feedback.
Yes, indeed. And before we go this week, we also have another very important announcement. We rely very heavily on donations from you, our loyal listeners, that keep this show on the road. Now, some of you already regularly support us and we are extremely grateful to you. It makes a huge difference because the contributions that you make enable us to pay our staff and continue to be creative and strive for the highest standards in science journalism. And I hope that we have demonstrated to you our commitment and passion for what we do this year, especially during the coronavirus pandemic. So if you are enjoying these programmes, please do help us, if you don't already, by making a contribution, or better still, becoming a regular supporter of The Naked Scientist. You can do that on our webpage. It's nakedscientist.com/donate. It's a highly secure system and the money comes directly to us. Thank you very much for considering this. The Naked Scientist comes to you from the Institute of Continuing Education at the University of Cambridge and it's supported by Rolls-Royce. I'm Chris Smith. Thanks for listening and until next time, goodbye.